Last time we talked about the pseudo-inverse, and I just want to add a short little lecture here talking about some of the properties of the pseudo-inverse. So, as you recall, given a matrix A with a singular value decomposition U sigma B transpose, we defined the pseudo-inverse as V sigma inverse U transpose. Like such. This is also called the Moore-Penrose inverse. And it's also called the natural inverse. And it's also called the Lanczos inverse, although the one I hear most frequently is the Moore-Penrose inverse. Okay, and we found that we had some really nice properties when we used the pseudo-inverse to a problem with either an infinite number of solutions or no solution, or the case actually where you have an infinite number of no solutions, in which case what I mean is we have an infinite number of ways to minimize the residual. In all of those cases, the pseudo-inverse solves y equals ax in general as x hat is equal to a dagger y. So let's just walk through and see some of these things. First, if A is invertible, then it has to be square. R equals M equal to N. Then A dagger is equal to A inverse. And we can easily check that because we would have A dagger times A would be V sigma inverse B transpose U sigma B transpose, which is just V sigma inverse sigma, and there would have been an n by n identity matrix in the middle there. And once again, if it's invertible, then all the singular values are going to be greater than 1, or greater than 0. And so we get V transpose is just equal to I. And the same thing works the other way, where we have A transpose is also equal to I. So it's both the left and the right inverse, and it's nice that it degenerates in that beautiful way. Next, the property is when A is more rows than columns, and has full rank, then we have something that's tall and skinny, right? So something like this. And so you'll have m in rows and columns. And what happens when we have this, we can just define a dagger as A transpose A inverse times A transpose. So, in this case, I guess I should put R is equal to N, and that's less than M. Because it's full rank, because R is equal to N, this works. So let's look at this in more detail. We'd have A transpose A is, this would be N by M, and that's M by N, and so the product is going to be N by N, and since it's full rank, there we go, we have invertible. So we could also continue this, write it out, and we have V sigma U transpose U sigma V transpose is equal to V sigma squared V transpose. And so now when we invert that, we get A transpose A inverse. We'll go ahead and multiply it by A transpose now. This gives us V sigma minus 2 V transpose. Then we multiply that by V sigma U transpose. That's our A transpose right there. And that's just V sigma inverse U transpose, which is indeed our A dagger as we defined it. So this is a nice handy way to do it, to find the pseudo inverse. The beautiful thing about finding the pseudo inverse in this case is you don't have to actually go through and calculate your SVD. So if you have your A matrix, maybe in some symbolic form or something like this, you can still come up with the pseudo inverse quite easily without going through the process of doing our singular value decomposition. Now when A has more columns and rows, we can get something very similar, but it is not the same expression. So in this case we have R is equal to M, which is less than or equal to N. Then we have that A transpose A is invertible, as we did before, and we find A dagger is equal to A transpose A transpose -1. So this happens when A is short and fat. So we can go through the same analysis that we did above in green and show that we do indeed get A dagger in this case. But you notice that this expression is different than the one above, mainly in it changes the order. A transpose is on the left, and then inside we have A transpose instead of A transpose A, because we're getting at the smaller of the two. We want the inside to be M by M so that it's full rank and invertible. When you're solving a problem, let's just look at how this works when we solve a particular problem. So let's assume that I had y is equal to ax, and a is m by n, with the case that m is greater than or equal to n, and its full rank. Meaning that the rank of A is equal to the smallest dimension of A. So we can't invert A because A is not square. But if we multiply both sides by A transpose, we get A transpose AX. And this is invertible. So we can then A transpose A inverse A transpose Y is equal to X. So just a demonstration of kind of the logic behind where we get those expressions and how that works. Okay, so just a little bit left. In the class notes, the PDF notes, it talks about this a little bit more and goes into the proof. But there's something else that's an interesting property of our pseudo inverse, and that is that if we define some matrix H and now we want to minimize over H. I guess I should put an R n by m. HA minus I, the Frobenius norm. So I guess inside the Frobenius norm essentially is defined like this. It's the sum of the squares of every element in the matrix. So when we're trying to minimize the Frobenius norm of this difference, HA minus I, we are trying to find the H, which when multiplied by A gives us something closest to the identity matrix. And it turns out that the minimizer is H equal to A dagger as we've defined it. And so this also works for the right inverse. That is the case when we're minimizing AH minus I Frobenius norm squared. So the moral is that our pseudo inverse is as close as you can get to an inverse of A. If we can't actually invert A, this comes really close to actually giving us an inverse of A. So this pseudo inverse is very, very useful, and in cases of full rank matrices, as you can see above, it's easy to compute. There's one other thing that's in the notes we won't cover, but it's relevant to this section, and that is the existence of the singular value decomposition. So you can look at that and find that yes, indeed, we can show that the singular value decomposition exists in a rigorous way, and you can see that in the notes.